Hello, everyone. Thanks for coming along. So I'm going to be talking about covert channels in TCP/IP. Imagine Alice is a spy working undercover, and she wants to leak out some information to Bob, but there's a warden watching. We'll call him Walter, and he's looking at every packet that's come out of Alice's machine, and if there's anything suspicious, then it's off to the shark tank. So Alice wants to get this information to Bob without being seen. She obviously can't communicate with Bob directly, but Bob is friends with one of the ISPs involved, so can see all information that's coming out of Alice's computer and going to one or more legitimate targets. To be more specific about the threat model, Walter can only see the traffic, but can't change this. And by communicating in violation of security policy, this is a covert channel. The way that Alice can do this is embed her message into the data that's transmitted to Bob, and this is called steganography. That comes from the Greek term of hidden writing, and there's been plenty of techniques for doing this. For example, you can write in paper with ink made out of lemon juice, and then when you warm it up, that will cause something to display. You can write in tablets and then cover them with wax, and these have been done throughout history, but I'm going to be looking at internet communications. So the first requirement of steganography is that the cover text is received intact. Obviously, if Alice breaks all internet communication, then she'll be spotted. But a further requirement is indistinguishability. This is where even if she's being watched and the warden knows all information about her operating system, all information about her current habits, then it should not be possible to differentiate that between any, normal behavior. And after the communication is taking place, she would like to communicate as much as possible, and that's called maximizing bandwidth. For those of you who don't know about TCP/IP, I'll give a very brief summary. The lowest level is Ethernet, and all that deals with is getting packets of information between one computer and another computer on the local network. Inside an Ethernet frame, you'll have an IP packet, and that deals with getting packets of information from one computer to another computer across the internet. What it doesn't do is give any guarantees that it's going to get there, and it also doesn't guarantee that it will be received correctly or in the same order. So that's where TCP comes in. This makes sure that packets are received in streams in order and they're not corrupted. And then on top of that, you can run protocols like HTTP, and this is an example of a web browsing request. So I'm going to be looking at TCP/IP. Firstly, I'll eliminate Ethernet. Ethernet frames only get between one computer and another computer on the local network. So it might be useful for some schemes, and there have been some interesting schemes using wireless communication and covert channels, but I'm dealing with the internet, so Ethernet's out straight away. There's also a large number of schemes that deal with higher levels, so HTTP, for example, email. You can embed information in these, and this gives you a very large amount of bandwidth, but the problem is Alice might not be able to control the application to run, so perhaps web browsing is okay, but email is not, or some combination of that. Alice doesn't even have to be a person. It could just be a process in a machine that's been hacked. So you've got your rootkit on another machine. You want to get the password list out of this, but you have a very good sysadmin who's watching every packet, and then you might get caught immediately. What you could do is, if this is a server, then each time that machine receives an incoming connection, on the outgoing connection, it will secretly hide a bit of information about passwords. Almost all applications use TCP/IP, so this is reasonably general, and Alice can use this, hopefully, without raising suspicion. So this is the IP header. I'll talk about the fields that are useful for embedding information. The first one to talk about are identification flags. These are for fragmentation. When you send a packet, IP packet on Ethernet or something like that, it's possible it wouldn't fit. Ethernet packets can be 64K big, and IP can be 64K, Ethernet is only 1.5K. So IP has the facility to split packets up, and this is called fragmentation. Firstly, every packet is given a unique ID. Each packet is given a unique ID, and then all the fragments are split up, and they keep the same ID so they can be merged. There's flags which say whether this has been fragmented, whether this is the first fragment or not, and the offset, which is which fragment or which byte index within the fragment. One way of encoding information is the size of fragments. There's no rule that says you have to fill an Ethernet frame. You could do something smaller. You could send a 1 could be lots of small packets, a 0 could be one big packet. You can reorder fragments. You can also reorder IP packets, but this is trivially detectable, even though it won't break the communication, because packets are very rarely reordered after the first few, and when they are, it's later on in the router stage and not on a particular host. And there's also TCP options. One is the TOS bits. This is for quality of service. You can say that this packet is high priority and should get through, or it needs low latency, or it needs high throughput. These are not really used. There is proposals to reintroduce them, the diffserv proposals, but for the moment, most operating systems set these to 0. So that means you can encode a lot of information, because these are ignored by almost everyone, but it's very detectable. And then there's flags. I mentioned that when you fragment a packet, if it's already below the maximum transfer unit, that's the maximum size of a packet that can go through a network, then it's not going to be fragmented anymore. But you can set a flag called do not fragment, and that's not going to make any difference to the way the information flows, but you can use that for signaling information. There are proposals to do that. Again, this is very detectable. Typically in TCP, all packets will come with the do not fragment bit set. Then there's IP options. One is the IP timestamp. This is almost never used because it greatly limits the path that IP packets can take. Another one is source routing. This is a favorite for hacking computers because you can redirect packets to take a route bypassing firewalls. But for this reason, this is now ignored, and quite often packets with these options set will be immediately dropped. The other one I mentioned was IPID, the one used for fragmentation. Initially, it seems that this could be very useful because in principle, it could be random. The only requirement for it is it's unique in order to properly reassemble fragments. The other requirement that's come more recently is you shouldn't be able to work out how many packets a host is sending based on the IPID. Previously, a lot of operating systems, Linux included, used a global counter, and that meant you could work out how many packets that machine had sent. So you'd ask it you send a ping and you get 1, you send another ping, you get 2, 3, 4. But if you start getting 5, 8, then you know it's sending packets in between. This is used by Nmap to do idle scanning. If you want to port scan a machine and you don't want to give out your identity, you choose a machine with a global counter as a victim. Then you send packets to the machine you want to port scan, but send the source address to your victim. And then you monitor how many packets that victim is sending out. The reason this works is when you send a packet to a machine with an open port, then it will send a reply to wherever you ask it to. If the port is open, then that machine will reply with, I never wanted this connection. If the port is closed, then it's not going to send anything. And using this way, it's called a stealth port scan. You can port scan a machine without ever directly giving away your IP address. Like I said, the only requirement of these is that it's unique, so you could quite easily put in arbitrary data in here, but this would be trivially detectable. If you look at the IP IDs coming from Linux, it is a per destination host counter, and this complies with the uniqueness requirements, and it also complies with bypassing idle scanning. You could set the initial value of the counter and use that for many information. That probably won't work, or you wouldn't be able to get very much information out of it, because the reason it's not going to work is it depends on TCP, which we'll come to later, and the reason you wouldn't be able to get much information out is that information on the counter is stored for quite a long time. So instead of going to look at TCP, the first one I'm going to look at is the options. There are many options. The most useful one for steganography is the TCP timestamp. This is not the same as IP timestamp, and it's embedded in every packet you send out is somehow your perception of the time. Then when a reply is sent to that packet, you get what you sent out in the first place, and this allows you to estimate the round trip time. There are also the flags. These have the same problem as IP flags. They're generally very predictable. There's the urgent pointer, which is, in principle, has a lot of capacity. If the urgent flag is not set, then you can put anything you like in urgent pointer, but Linux does not do this, so you immediately spot that. So I'll go back to TCP timestamp. This is mostly predictable. You can estimate the clock of another machine. But the least significant bit, at least in the slow network, is more or less random, or at least you'd hope. This means you can send out information in this least significant bit. There is a scheme which does this called devcc. It's been implemented for the Linux kernel, and for low bandwidth connections, it's probably hard to detect, although not impossible. The difficulty comes in high bandwidth connections. If you can send many packets, or normally send many packets, in one tick of the clock, then if you want to send, say, a 0, and the timestamp coming up ends in a 1, then you have to stop sending, and vice versa for 1s. This means you have to slow down your internet connection. On average, you can only send 2 packets per clock tick. Slow connections, that's fine, but on fast connections, this will be detected. So the one I'm going to emphasize for the rest of the talk is the TCP initial sequence number. When you first make a TCP connection, both sides pick a number. Assume it's random for now, and that's called the initial sequence number. Thereafter, every packet in this connection contains that initial sequence number plus the number of bytes transferred so far. This allows, firstly, reliability. If you see a jump that's unexpected, then that means a packet's been lost and you can request it be transmitted. If you start seeing packets in the wrong order, then they're in the wrong order, and you can reassemble these into an appropriate stream. The other requirement is that the initial sequence number is hard to guess for hosts that are not involved in the conversation. This is necessary because one of the properties of TCP is it should be hard to spoof. So if I make a connection and then spoof my source address, I shouldn't be able to carry on that connection. The way this works is you have to do something called a three-way handshake in TCP. You have to send a packet to the remote host, it will send something back, and then you reply to that. The one it sends back will have the opposite side's initial sequence number. You then have to send that back in order for the TCP connection to succeed. If you spoof your source address, you'll never get that packet, and the connection will be pulled down. But if you can guess what it's going to be, because it's not a random number, then you can keep on carrying on this communication. You can spoof a source address. Perhaps you can spoof the source address as an IP address inside this network. And up till quite recently, a lot of services used IP-based authentication, for example, R-shell. And this will allow you to run arbitrary commands on hosts you shouldn't. This isn't much of a problem now. Most hosts, or most desktop operating systems, now know how to produce non-random, non-predictable IP TCP initial sequence numbers. There are some problems with embedded hardware. The reason it might be useful for steganography is, firstly, it's big. It's 32 bits compared to the IP ID, which is only 16. And if it's unpredictable to everyone not involved, then it's also unpredictable to the warden. Remember, he knows the operating system, but he doesn't actually have access to the computer. And there's been a variety of proposals for using this, but doing it is a lot harder than you might expect. I'm going to talk about some schemes that have been proposed and how they slip up, and then I'm going to propose how this can be fixed. The first one is NUSHU. This is proposed at the last Scale Communication Congress, and this is what got me interested in this subject. It's been implemented for Linux. It's a very clever scheme. It has reliability. So when you send out a packet, firstly, there's reliability information embedded in it. Like a small version of TCP, it has a packet number, and that means if packets are lost or reordered, you can reassemble it, and then it's encrypted. And then there are tricks in the Linux kernel which hide it from someone who's on localhost trying to inspect it. What I'm going to look at is not the localhost detection, but ones on the network. The reason encryption is used is to make the initial sequence numbers look random, and on a first glance, they are unpredictable. You would think that because they're unpredictable, that they're going to be random, but in fact they're not. So here's a graph comparing Linux and NUSHU. The first thing you'll notice, I'll explain what the axes are. On the x-axis is a particular initial sequence number. On the y-axis is the following initial sequence number. The first thing to notice about Linux is the scale. It doesn't use anywhere near the whole space of initial sequence numbers. It only goes up, everything starts with 9, but it's fairly evenly distributed above that. The red dot in both axes is the mean for that axis. The other thing to notice is there are not large changes. So there's nothing in the top left-hand corner and the bottom right-hand corner, and those are the ones that signify changes. If you compare it to NUSHU, here it's very evenly distributed, and it uses almost the whole space. So it's probably possible to detect NUSHU just from doing this analysis, but it should be possible to do better. This is how NUSHU encrypts packets, initial sequence numbers. The requirements from this are the initial sequence number output should look random, and it should be possible to decrypt every packet by itself. This is because packets might be lost, and you don't want to rely on everything being received correctly before you can decrypt anything. The other problem is most block ciphers, like DES, which is being used here, are 64 bits up. AES is a 128-bit block, and that means it can only encrypt that size or some multiple thereof. So instead of using it in normal mode, it first takes the source port and destination port, the source address and destination address, and XORs these together. It appends NU to pad it up to the appropriate length, and then it encrypts this using the secret key that's shared by Alice and Bob, and this gives you another 64-bit output. Because you only want 32 bits, that's how large an ISN is, you XOR your message along with all the reliability information with that, and you get the new initial sequence number. The problem with this is there's going to be frequent duplications of the of the highlighted fields. The source IP address is not going to change for most hosts. It's pretty much fixed. The source address there's not going to be much variation in those. Destination port, if you're doing a lot of web browsing, that will always be 80. The worst case is if you're using a web proxy, then the destination address is always going to be the same. The port is always going to be 8080. The source address is always going to be the same, and you've only got the port number, the source port number left. At best, that's going to be 16 bits. In practice, it's going to be a lot less. When I've been looking at some packet dumps, in practice, about half of the packets you receive are going to be duplicated in this way. In order to understand why this is a weakness, I'll give you a very brief background of XOR. If you take a number and then XOR it with itself, you get 0. And all that means if you take a message, you encrypt it with a key, you take another message and encrypt it with the same key, and then XOR those two, then the result will be the two messages XORed with each other. And if both of these messages are the same, the result is going to be 0. But even if they're not, you can still pick up patterns. For example, assume the message is all ASCII. In ASCII bytes, the top bit is always 0. That means when you XOR two ASCII bytes, the top bit of that is always going to be 0, and there are similar patterns for anything else you can find. And this is the result. This is slightly different from the previous graph. The x-axis is still the current initial sequence number, but the y-axis is the next packet with the same initialization vector. That's the same source port, destination port, source IP address, and destination IP address. And on Linux, this is more or less random, apart from the limited the limited range. But I think it's clear that no-shoot is easily detectable. This is because all packets were sent with the empty byte. So that meant that they weren't all 0, but they were all the same, and that's what this graph shows. It's possible to avoid this, for example, by eliminating the repeated IV problem. You could hash more of the header, and that will give you a bit more randomness. You could use a different style of block cipher. But that will only work if initial sequence numbers are random. But if you look at how Linux generates them, it's not quite the same. The requirement for initial sequence number should be unguessable by people not involved in this conversation. And the conversation is defined by the source, destination, port, and IP address. So what Linux does is put these 3 bytes into 32 bits, and then I'll also add a random number to bring it up to 4 bytes. Then it takes a reduced version of MD4. This is a hash function. You feed it a variable length input, and it will give you something which depends on that, but shouldn't be possible to map back. And it also throws in 256 random bits. This is only known by that host. And then you take the second byte, from that, because you, and then, sorry, the second 32 bits. Then you replace the first byte with a counter, and then add on the time. The reason you have a counter is MD4 is known to be weak, so acting conservatively, the key, the 256 random bits, is changed every 5 minutes. But once you change that key, it's possible that you're going to get something very similar to the last initial sequence number, and then you might risk a collision. So replacing the counter at the beginning, which is incremented on each rekey, should hopefully prevent that. And then the reason you add time is it's possible a TCP connection will be recycled. If it's cancelled and then retried, you don't want to use the same initial sequence number in case the packets are still on the internet. You want to be able to differentiate the dead connection from the live one. And so you add the time in microseconds. This is going to lead to some patterns. If you have the same rekey period, in the same rekey period, you're going to have the same key. And if you have the same initialization vector, that is source destination port and IP address, then the input of MD4 is going to be the same. The key is the same, so the output is going to be the same as well. That means that all you have left is this timer, and the difference between two initial sequence numbers is going to be the time in microseconds. That means that even if you fix the problems that Nushu had, adding a bit more randomness, and if you ever see you're going to send the same data with the same initialization vector, you do something different, then you'll never have the collisions that I showed before, but it will look random, but Linux doesn't look random. So on the left-hand side is what Linux would look like, or Linux does look like. I've tried to send packets out as fast as possible, all with the same source port, destination port, source IP address, and destination IP address. And they're all more or less clustered on the left-hand side of the graph because the Linux was able to send about one packet every 2 milliseconds. But on the y-axis, I've stored the difference in initial sequence numbers. And you can see in Linux, there's very good correlation. And in fact, if you look at, say, the packets at 3 milliseconds, that corresponds to a difference of about 3,000. That's because that's because the difference is due to that 1 megahertz counter, which corresponds to microseconds. If, on the other hand, you randomize the initial sequence number, like a good cryptographic function would do, then you still have the clustering on the x-axis, because that's when the packets were sent, but they're very evenly distributed on the y-axis, and this would be trivially spottable. In order to do good steganography for Linux, you have to emulate as closely as possible the way real initial sequence numbers are generated. The difference is you want to be able to get the information back out, whereas Linux is designed for the exact opposite. The way I propose to do this is you take the lower 3 bytes of the initial sequence number and replace that with your data. If you remember, comes from MD4, so is hopefully unpredictable. You can't do anything about the top byte. That's where the rekey counter has to be, so you put that there. Then you also have to worry about what will happen when the time was added on. This might cause a carry into the rekey counter, which the attacker would be able to see. So you compare the current time in microseconds with the data you added, and if the result is negative, then you add one to the rekey counter. And that should hopefully patch all that up. Then you also have to correct the checksum, and also the IP ID. I mentioned that this is a counter. In the case of TCP, the initial value comes from the TCP initial sequence number. There's no reason for this, but it's as good as anything else. But if you assume that the initial sequence number is random, and the attacker is aware of how Linux does this, then you can be caught out. You have to worry about packets being lost. IP packets get lost all the time. But in the case of a TCP connection setup, if the connection succeeds, you'll see an ACK back. If not, then you can assume that packet was lost. But you still have to make sure that what is coming out of MD4 really is random. So you have to achieve freshness using a good initialization value. Instead of just XORing the source destination port IP address, you put that into a hash function, and that dramatically reduces the number of collisions. That should only be about 1 out of 50,000. And whenever you see that you are going to have a collision, then you make sure that you're never sending the same data. If you are, then you set a flag in your data that this is not real data, and then you encrypt a counter. And that means the attacker, without knowing your key, wouldn't be able to understand that steganography is taking place. So the same idea works for OpenBSD. It has a very different way of generating initial sequence numbers. There's nothing to do with connections. There's just one global setup. Once the requirement is that there should be no two consecutive initial sequence numbers which are close to each other, then you have problems of collision. The way it achieves this is for the first half of the 32 bits, it takes a counter and then encrypts that using a block cipher. One of the properties of a block cipher is you will never get duplicates in output if you don't have a duplicate in input. And with a counter, it means that you get, in this case, 2 to the 15 before you see any collisions in the output. But given any of those, you shouldn't be able to predict the next one without knowing this 1024-bit random key. Just like Linux, it rekeys also every five minutes, and that's what the top bit is for. The rekey, rather than a counter, it's just a bit. And this means that when a rekey happens, you will never have two outputs that are very close to each other. The bottom half is replaced with some output of RC4, which is the random number generator that OpenBSD uses. This is not block cipher, it's a stream cipher, so there can be collisions. The other thing that's added is a 0 in between the block cipher output and the RC4 output. This is because the RC4 output could change from all ones to all zeros, and the block cipher could change from all zeros to all ones. And then you'll have, without that 0, two initial sequence numbers that differ only by 1. With the 0, you guarantee that they're more than 2 to the 15 apart. Again, if you want to encode steganography in Linux and OpenBSD, you follow that. RC4 is easy. It looks like random numbers, so that's exactly what you put there. You do the standard tricks to encrypt your message and make sure it looks like random, and then you embed that into the bottom 15 bits. The top 15 bits is harder. The guarantee that a block cipher gives you is there's never going to be repetitions, whereas if you're encrypting different messages, if you encrypt the same message twice with the same initialization vector, you will get the same thing out, and that should never happen. So what you have to do is encode arbitrary data into a pseudo-random sequence, such that there's no duplicates. This starts off as being easy to do, but the problem that comes in is there might be packet loss. And the obvious ways of doing this mean that as soon as you lose one packet, then you lose everything. So in the associated paper, I show the algorithm that is used for doing this. And now for something completely different, or at least it seems that way. There's been a recent paper which shows that many machines have different clock skews. This is because every machine has a clock crystal in them, and they're not all perfect. Over time, they will drift away from each other. They're also very stable. So if you're off by 1 millisecond per second now, then if you go to a different country, then you're probably going to be off by 1 millisecond per second. This means that if you take your laptop to an access point here, and then you want to become untraceable and you take your laptop somewhere else, you make sure you're not using any of the same applications, and you're obviously using a different IP address, then to a certain extent you can still be tracked. This graph shows a collection of TCP timestamps from a few machines I've accessed, and you can see that they do differ by a significant amount, and a measurable amount after 400 seconds. There's a significant amount of noise. In the top ones, you can see that there's rough edges, but in the bottom ones, there's a lot of noise. This is because TCP timestamps can vary in speed. There's nothing in the specification that says how fast they are, just that their time. They can vary between 1 hertz and 1 kilohertz. In the case of Linux, I think it's between 100 hertz, and those are the bottom ones, and 1 kilohertz, which are the top ones. So I'm interested in reducing the amount of noise. I mentioned that when Linux generates initial sequence numbers, it adds on the time in microseconds. So that's a 1 megahertz clock, 1,000 times faster than the TCP timestamp. Another option is the ICMP timestamp. This is where you send a packet to a machine, and then you'll get a request, a reply, which is the time in 1 kilohertz. You'll notice this is the same number of machines as last time, but there's a lot less variation. In fact, all the machines that were NTB synchronized have been clustered into those middle bars. That's because the timestamp that's used in TCP for the TCP timestamp happens before the NTB synchronization, whereas with ICMP, this happens from the get time of day system call. So you'll remember this graph from before. This is where I showed that Linux uses time information when it's generating initial sequence numbers. And also I pointed out that if you look up from the packet sent with 3 milliseconds different, you'll get to 3,000, and that corresponds to microseconds. There is a subtle difference here. The time difference on the x-axis is time according to when the packet is received, and the initial sequence number is the time according to the machine that sent it. That means you can use this to estimate the clock skew. And here's the output of that. And first you'll notice that it has the same problem with NTP, but it's a lot smoother. And this does give some options for avoiding the NTP problem. NTP is designed not to track short-term changes. It takes about 6 hours once it detects that the clock is probably incorrect before it corrects that. That's to stop it chasing the air conditioning, because a clock crystal will change its speed subtly when the temperature changes. That means that if you zoom into these graphs, you'll be able to see that the clock skew changes, and then the NTP will synchronize it. You also have to worry with the initial sequence number that there's going to be rekeys. This is quite hard to deal with because it's perfectly possible for the initial sequence number not to change when there's a rekey. The other thing that's a lot easier to handle with is when there's overflows. An initial sequence number is only 2 to 32 bits, and when you have a 1 megahertz clock, it is going to overflow. That's very easy to detect. As soon as you see 2 packets from the same source destination port IP address that go from a high number to a low number within a rekey period, then you know that there's been an overflow. Okay, so in conclusion, there's many proposed steganography schemes that are detectable. The main reason is that they look at the specification, which says that this field can be anything, it could be random, and then assume, because it looks vaguely random, it is random. In fact, this isn't the case. In the case of Linux, the initial sequence number is not random for very good reasons. That's to stop collision. The IP ID is not random for random reasons. And if you want to build a undetectable steganography scheme, because you're worried about someone watching the network traffic, then you have to follow the specification backwards and make sure there's no way of detecting that. So if you look at the paper I've got associated with this, it's not in the proceedings, but it is in my website, then I've got a suite of tests that should tell the difference between random data and appropriate IP IDs and initial sequence numbers. This could also be used for fingerprinting. And the other thing I mentioned was the physical device fingerprinting. If you think you're untraceable because you move your computer to a different continent, then that may well not be true. If you're worried about someone fairly powerful tracking you, then this should be a concern. You could try to turn off all sources of timing information. The obvious ones are ICMP timestamps are easy to turn off, as are TCP timestamps, but initial sequence numbers aren't. So you could look at options like the OpenBSD randomization of sequence numbers firewall. That has some possibilities, but I'm looking at other ways to extract timing information even from that. So if you're worried about that, you have to make sure that there are no sources of timing information that you don't expect. So I'll finish a bit early now, but I'm happy to answer any questions. Thanks.
I guess my question is pretty simple in the end. Where is all this being used?
That's a good question. I am not aware of any case where a covert channel in the computer system has been used for profit, with the only exception is a project I did a couple of years ago where I slightly bent the rules in a programming competition in order to win an Xbox using a covert channel. And despite there being a lot of concern in the military for covert channels, since the 90s there's been billions of dollars spent on trying to remove covert channels. I don't know of one case where they've actually been used. But if people were using them, they probably wouldn't say.